Hi class, today we will discuss where the Davis-Besse nuclear power station is located and what benefits it has provided. We will also discuss the errors made by the team at Davis-Besse and how the stress corrosion cracking occurred. The Davis-Besse nuclear power station first started producing power in 1977 and was Ohio's first nuclear power plant. The plant is located 35 miles outside of Toledo, Ohio, and produces about 40% of the electricity for businesses and industries within northwestern Ohio. The plant contributes more than $6 million annually to local and state taxes and employs more than 700 full-time employees. Along with state tax contributions and employment opportunities, Davis-Besse owns 733 acres designated as protected wetlands that are used for major migratory pathways for birds and home to bald eagles. The NRC required all reactors to have inspections of the reactor pressure vessels completed by December 31st, 2001. However, the NRC granted the Davis-Besse operators a delay for the inspection until February of 2002. The inspection began in 2002 when the Davis-Besse station shut down for refueling. During the refueling, a cavity was found that had eaten through 6 inches of the reactor pressure vessel. It was determined the cavity was the result of corrosive coolant from the reactor core. The pressurizer within the RPV is comprised of heater spray freezing the water temperature within the reactor, and water sprays to allow for steam volume and condensing and lowering pressure. The hot pressurized water is transferred to the steam generator via pipes, where it is converted into steam to drive the turbines for generating electricity. The issue that was found was determined to be partly due to the Davis-Besse station workers not having a focus on safety. Roger Whitcomb, who was brought on in 1985 to help investigate an incident of feedwater loss through steam generators, was interviewed, and he stated for 2.5 years he worked at improving maintenance at Davis-Besse. In June 1988, he submitted a 75-page report that identified improvements and provided critical assessments of where workers needed to go with preventative maintenance. He said management was not happy with the report and even ordered him to change the report rather than actually changing the issues. When Whitcomb heard about the hole in the reactor, he stated that it was systematic of the same pattern of behavior and disregard for safety that occurred in the 1980s. Stress corrosion cracking is a significant material degradation for major components of both pressurized water reactors. There are different forms of aging, which include pure irradiation-induced hardening and softening, irradiation-induced swelling, phase transformation, creep, and thermal aging. Thermal aging and low cycle fatigue, and high cycle mechanical fatigue due to flow-induced vibration, chemical corrosion related to damage such as flow-assisted general corrosion, crevice corrosion, and stress corrosion cracking. The different forms of aging can act individually or in combination to hasten the aging process. Different nuclear power plant components are subjected to different mechanisms that can cause damage. These mechanisms are dependent on the type of materials used, the way it is manufactured, and the different exposure environments. Reactor pressure vessels may be subjected to fatigue damage that support the reactor core, maintain fuel assembly alignment, and other things. These internal structures are subjected to reactor coolant water chemistry, higher temperature, and a higher radiation dose compared to the reactor pressure vessel shell. Major possible degradation mechanisms for these internal components are irradiation embrittlement and associated irradiation-assisted stress corrosion cracking. For longer-term operation, potential causes of aging include high cycle fatigue due to flow-induced vibration and low cycle thermal fatigue. Internal case steel components may also see thermal embrittlement. Stress corrosion cracking is a major issue for steam generator tube integrity in many U.S. pressurized water reactors. The primary cause of stress corrosion cracking is the residual stress created in the component during manufacturing or fabrication processes. Major concerns for the reactor cooling systems are stress corrosion cracking and stress-induced low cycle fatigue due to thermal and pressure changes. Pressure and thermal stress are created during system transients, including heat up and cool down, that could cause low cycle fatigue damage. The low cycle fatigue is a combination of stress corrosion cracking can lead to corrosion fatigue. The discovery of the cavity occurred while the plant was shut down for refueling. During the shutdown, the licensee was conducting inspections for reactor pressure vessel head penetration nozzle cracking caused by primary water stress corrosion cracking. During these inspections, the licensee discovered cracks in several vessel head penetration nozzles, which are made of nickel-based alloy. The vessel head penetration nozzles are part of the reactor coolant pressure boundary in pressurized water reactor plants. The vessel head penetration nozzles are known to be highly resistant to general corrosion, but are susceptible to primary water stress corrosion cracking. Borated water is used in pressurized water reactor plants as a reactivity control agent to aid in control of nuclear reaction. If leakage occurs from the reactor coolant system, the escaping coolant flashes to steam and leaves behind a concentration of impurities, including the boric acid. Boric acid can cause extensive and rapid degradation of carbon steel components. Vessel head penetration nozzle leakage, if undetected and uncorrected, could potentially lead to failure of a nozzle and result in loss of coolant accident. The cracking of vessel head penetration nozzles was first observed at a French pressurized water reactor, Bougie Unit 3, in 1991. As a result of the Bougie experience, the NRC implemented an action plan to address primary stress corrosion cracking of vessel head pressurized nozzles fabricated from alloy 600. This action plan included an NRC staff review of safety assessments conducted by the pressurized water reactor owners groups. Subsequently, inspections led to the discovery of extensive circumferential cracking of several vessel head pressurized nozzles at Oconee Nuclear Station, Unit 3, in the spring of 2001. The cracking is severe enough. Circumferential cracking in vessel head pressurized nozzle is a large safety concern than axial cracking, since it creates the potential for separation of the nozzle. As a result of the ONS cracking experience, the NRC issued a bulletin which requested licensees to address the potential for similar cracking at their plants and to discuss their plans for vessel head pressurizer nozzle inspections. It also recommended vessel head pressurizer nozzle inspections be performed by December 31st, 2001 for plants that were highly susceptible to circumferential cracking. The Babcock and Wilcox plants, such as ONS and Davis-Besse, were all considered to be highly susceptible to the potential for circumferential cracking. By the end of November 2001, all but one of the other Babcock and Wilcox units had identified circumferential cracking of vessel head pressurizer nozzles. Again, the Davis-Besse plants was able to convince the NRC to delay their inspections until February. Had the inspection been completed on time, the corrosion would not have been as bad. If they had focused on safety and not necessarily making the extra cleaning, maybe the repairs would not have been as vast. I hope you were able to learn a little bit about where the Davis-Besse nuclear power station is located and what benefits it has provided. I also hope that you have learned about the errors made by the team at Davis-Besse and how the stress corrosion cracking occurred, and know what to look for when you begin working for a power plant.